Hello, everyone. I am Professor Hua from the Communication Engineering Teaching and Research section at Wuzhou University, and welcome you to this mini lecture. Today, we will cover Chapter 1, Section 1, Classification of Signals in Systems. Next, we will learn this section's content through the following aspects. First, we will discuss the classification of signals. Signals can be classified in various ways. There are mainly four categories: deterministic signals and random signals, continuous time signals and discrete time signals, periodic signals and non-periodic signals, energy signals and power signals. We will explain each of these four classifications in detail below. The first classification method for signals is deterministic signals versus random signals. A deterministic signal refers to a signal that can be represented by a definite function of time, such as the sinusoidal signal shown in the figure below. A deterministic signal can be expressed by a precise functional form. A random signal, also known as a non-deterministic signal, is not a definite function of time. Unlike a deterministic signal, a random signal cannot be represented by a precise mathematical expression. Such signals are usually analyzed using probability and statistical methods. For example, noise is a typical random signal. In this course, we will focus on deterministic signals, and random signals are generally studied at the graduate level. The second classification method for signals is continuous time signals and discrete time signals. A continuous time signal is defined over a continuous range of time in the observation process and has definite values, allowing for a finite number of discontinuities in its time domain. It is usually denoted as f of t, as shown in the figure. A discrete time signal, on the other hand, is defined only at specified discrete instance and is usually denoted as f of k, as illustrated in the lower right figure. The distinction between continuous time signals and discrete time signals is based on the values of the time variable. Continuous time signals have time values that are continuous, whereas discrete time signals have time values only at integer positions. Please note that these integers physically represent integer multiples of the signal's sampling period. On the time axis of a discrete time signal, the signal amplitude is undefined at non-integer positions and should not be mistakenly interpreted as zero. Moreover, if a continuous time signal also has continuously variable amplitudes, it is called an analog signal. Conversely, if a discrete time signal also has discretely variable amplitudes, it is called a digital signal. In this course, when we refer to signals, we emphasize only the continuity or discreteness of the time variable, without placing much emphasis on the amplitude variation. Therefore, the concepts of analog and digital signals will not be frequently mentioned in this course. The third classification method for signals is periodic signals and non-periodic signals. For a continuous time periodic signal, there exists a non-zero real number t, such that f of t plus t equals f of t, hold for all t. The smallest positive t satisfying this condition is called the fundamental period of the continuous time signal. For example, the sinusoidal signal mentioned earlier is a typical continuous time periodic signal. Similarly, for a discrete time periodic signal, there exists a non-zero integer, n, such that f of k plus n equals f of k, holds for all k. The smallest positive integer, n, satisfying this condition is called the fundamental period of the discrete time signal. The periodicity of discrete time signals will be discussed in detail in later chapters, so we will not elaborate further here. Moreover, signals that do not satisfy the definition of periodic signals are called non-periodic signals. In other words, Signals are either periodic or non-periodic, and most of the signals discussed in this course are non-periodic. The fourth classification method for signals divides signals into energy signals and power signals. First, let's explain signal energy and power. In this course, energy and power refer to normalized energy and power. That is, the power dissipated by current or voltage across a 1 ohm resistor. The formulas for calculating the normalized energy and power of continuous time signals and discrete time signals are given by the following 4 equations. Please note that the energy and power calculations for continuous time signals are performed using integrals, whereas for discrete time signals, they are performed using sums. For the derivation and origin of these 4 formulas, please refer to the relevant textbooks on circuits and signals and systems. We will not elaborate here. Now, let us specifically explain the definitions of energy signals and power signals. An energy signal is one with finite energy and zero power, while a power signal is one with finite power and infinite energy. In other words, some signals can only be expressed and analyzed from the perspective of energy, while others can only be analyzed from the perspective of power. For example, a non-periodic signal of finite duration is a typical energy signal, whereas a direct current signal and periodic signals are typical power signals. Please note that this classification is not mutually exclusive in the sense that a signal cannot be both an energy signal and a power signal. However, there are signals that are neither energy signals nor power signals, such as exponential signals. After class, you can refer to examples or exercises in the relevant reference textbooks to gain a deeper understanding of this classification method. Next, let us discuss the second major topic of today's lecture: classification of systems. There are many ways to classify systems. This course will focus on the following 5 methods. First, continuous time systems and discrete time systems. Second, linear systems and nonlinear systems. Third, time invariant systems and time varying systems. Fourth, causal systems and non-causal systems. Fifth, stable systems and unstable systems. The first classification of systems is continuous time systems versus discrete time systems. A continuous time system is one in which both the input excitation and the output response must be continuous time signals, whereas a discrete time system is one in which both the input excitation and the output response must be discrete time signals. Systems are generally depicted using block diagrams. In this course, we typically use simple rectangular blocks, as shown in the figure, in addition to block diagram representations. The mathematical model of a continuous time system is a differential equation, while that of a discrete time system is a difference equation. These topics will be discussed in detail in Chapter 3. Although real-world systems can be quite complex, both continuous and discrete systems are ultimately composed of only 3 basic building blocks. As illustrated in the figure, a continuous time system is built from adders, integrators, and multipliers, whereas a discrete time system is built from adders, differencers, and multipliers. Note carefully the distinction between an integrator and a differencer. Continuous signals admit only integration operations, while discrete signals admit only differencing operations. The second classification method for systems is linear systems versus nonlinear systems. A linear system is one that exhibits linearity, which comprises both homogeneity and superposition properties. Both properties must be satisfied simultaneously, or the system is nonlinear. The homogeneity and superposition properties can each be expressed mathematically. We will cover the criteria for system linearity in the next subsection. The third classification method for systems is time-invariant systems versus time-varying systems. Observe the continuous time signal f of t and its delayed version f of t minus t0 passing through the same system, and compare how the waveforms change. From a figure, when a signal is delayed by t0 before entering the system, its waveform remains unchanged compared to the undelayed case, and the input delay equals the output delay. We thus conclude that such a system is time-invariant, or non-time-varying. Therefore, we can summarize the concept of time variance in a system as follows. If the relationship between the system's input excitation and its output response remains unchanged regardless of the time at which the input is applied, the system is called time-invariant. Otherwise, it is time-varying. The mathematical expressions for a system's time variance are given below. In the next subsection, we will provide a detailed discussion on how to determine a system's time variance. The fourth classification of systems is between causal systems and non-causal systems. A system is causal if and only if it produces an output response only when the input signal excites it. That is, the output cannot occur before the input. Otherwise, the system is non-causal. The fifth classification method is stable systems versus unstable systems. A stable system is one in which every bounded input produces a bounded output. Otherwise, it is unstable. Please reflect on today's lecture and complete the following homework exercises to consolidate the concepts learned and deepen your understanding. This concludes Section 1 of Chapter 1. See you in the next mini lecture.